Stanford University.
Good morning. So it's 12:03, so I want to get started. Welcome to Lecture 12 of CS2-1N. Today we're going to talk about visualizing and understanding convolutional networks. This is always a super fun lecture to give because we get to look at a lot of pretty pictures. So it's one of my favorites. As usual, a couple administrative things. So hopefully your projects are all going well because, as a reminder, your milestones are due on Canvas tonight. Wait, it is Canvas, right? Okay, just want to double check. Yeah, due on Canvas tonight. We're working on furiously grading your midterms, so we'll hope to have those midterm grades to you back on Gradescope this week. So I know there was a little confusion. You all got registration emails for Gradescope probably in the last week, something like that. We saw a couple questions on Piazza. So we've decided to use Gradescope to grade the midterms, so don't be confused if you get some emails about that. Another reminder is that Assignment 3 was released last week on Friday. It'll be due a week from this Friday on the 26th. Assignment 3 is almost entirely brand new this year, so we apologize for taking a little bit longer than expected to get it out. I think it's super cool. A lot of the stuff that we'll talk about in today's lecture, you'll actually be implementing on your assignment. And for the assignment, you'll get the choice of either PyTorch or TensorFlow to work through these different examples. So we hope that that's a really useful experience for you guys. We also saw a lot of activity on HyperQuest over the weekend, so that's really awesome. The leaderboard went up yesterday. It seems like you guys are really trying to battle it out to show off your deep learning neural network training skills, so that's super cool. Due to the high interest in HyperQuest and due to the conflicts with the milestone submission time, we decided to extend that deadline for extra credit through Sunday. So anyone who does at least 12 runs on HyperQuest by Sunday will get a little bit of extra credit in the class. Also, those of you who are at the top of the leaderboard doing really well will get maybe a little bit extra credit. So thanks for participating. We got a lot of interest, and that was really cool. Final reminder is about the poster session. So the poster session will be on June 6th. That date is finalized. I don't remember the exact time, but it is June 6th, so that we had some questions about when exactly that poster session is for those of you who are traveling at the end of quarter or starting internships or something like that. So it will be June 6th. Any questions on the admin notes? No? Totally clear. So last time we had a pretty jam-packed lecture where we talked about a lot of different computer vision tasks. As a reminder, we talked about semantic segmentation, which is this problem where you want to assign labels to every pixel in the input image, but does not differentiate the object instances in those images. We talked about classification plus localization, where in addition to a class label, you also want to draw a box or perhaps several boxes in the image, where the distinction here is that in the classification plus localization setup, you have some fixed number of objects that you're looking for. So we also saw that this type of paradigm can be applied to things like pose recognition, where you want to regress to the different numbers of joints in the human body. We also talked about object detection, where you start with some fixed set of category labels that you're interested in, like dogs and cats, and then the task is to draw boxes around every instance of those objects that appear in the input image. And object detection is really distinct from classification plus localization, because with object detection, we don't know ahead of time how many object instances we're looking for in the image. And we saw that there's this whole family of methods based on RCNN, fast RCNN, faster RCNN, as well as these single-shot detection methods for addressing this problem of object detection. Then finally, we talked pretty briefly about instance segmentation, which is kind of combining aspects of both semantic segmentation and object detection, where the goal is to detect all the instances of the categories we care about, as well as label the pixels belonging to each instance. So in this case, we detected 2 dogs and 1 cat, and for each of those instances, we wanted to label all the pixels. So these are, we kind of covered a lot last lecture, but those are really interesting and exciting problems that you guys might consider using in parts of your projects. But today we're going to shift gears a little bit and ask another question, which is what's really going on inside convolutional networks? We've seen by this point in the class how to train convolutional networks, how to stitch up different types of architectures to attack different problems. But one question that you might have had in your mind is what exactly is going on inside these networks? How do they do the things that they do? What kinds of features are they looking for? And all these sorts of related questions. So far we've sort of seen ComNets as a little bit of a black box where some input image of raw pixels is coming in on one side. it goes through many layers of convolution and pooling and different sorts of transformations. And then on the outside, we end up with some set of class scores or some type of understandable, interpretable output, such as class scores or bounding box positions or labeled pixels or something like that. But the question is, what are all these other layers in the middle doing? What kinds of things in the input image are they looking for? And can we try to gain intuition for how ConvNets are working, what types of things in the image they're looking for, and what kinds of techniques do we have for analyzing these internals of the network? So one relatively simple thing is the first layer. So we've talked about this before, but recall that the first convolutional layer consists of filters that, so for example, in AlexNet, the first convolutional layer consists of a number of convolutional filters. Each convolutional filter has shape 3 by 11 by 11, and these convolutional filters get slid over the input image. We take inner products between some chunk of the image and the weights of the convolutional filter, and that gives us our outputs after that first convolutional layer. So in AlexNet, then we have 64 of these filters. But now in the first layer, because we're taking a direct inner product between the weights of the convolutional layer and the pixels of the image, we can get some sense for what these filters are looking for by simply visualizing the learned weights of these filters as images themselves. So for each of those 11 by 11 by 3 filters in AlexNet, we can just visualize that filter as a little 11 by 11 image where the 3 channels give you the red, green, and blue values. And then because there's 64 of these filters, we just visualize 64 little 11 by 11 images. And we can repeat this exercise. So we've shown here so these are filters taken from the pre-trained models in the PyTorch model zoo. And we're looking at the convolutional filters, the weights of the convolutional filters at the first layer of AlexNet, ResNet 18, ResNet 101, and DenseNet 121. And you can see kind of what these filters are looking for. You see that a lot of things are looking for oriented edges, like bars of light and dark at various angles and various positions in the input. We can see opposing colors, like this green and pink opposing colors, or this orange and blue opposing colors. So this kind of connects back to what we talked about with Hubel and Weasel all the way in the first lecture. That, remember, the human visual system is known to detect things like oriented edges at the very early layers of the human visual system. And it turns out that these convolutional networks tend to do something somewhat similar at their first convolutional layers as well. And what's kind of interesting is that pretty much no matter what type of architecture you hook up or whatever type of training data you train it on, you almost always get the first layers of the first convolutional weights of pretty much any convolutional network looking at images ends up looking something like this, with oriented edges and opposing colors looking at that input image. But this really only, oh, sorry, was there a question? Yeah, so these are showing the learned weights of the first convolutional layer. Oh, so the question is, why does visualizing the weights of the filters tell you what the filter is looking for? So this intuition comes from sort of template matching and inner products, that if you imagine you have some template vector, and then you imagine you compute a scalar output by taking an inner product between your template vector and some arbitrary piece of data, then the input which maximizes that activation under a norm constraint on the input is exactly when those two vectors match up. So in that sense, that whenever you're taking inner products, the thing that causes an inner product to excite maximally is a copy of the thing you're taking an inner product with. So that's why we can actually visualize these weights, and why that shows us what this first layer is looking for. So for these networks, the first layer is always a convolutional layer. So generally, whenever you're thinking about image data and training convolutional networks, you generally put a convolutional layer at the first step. Yeah, so the question is, can we do the same type of procedure in the middle of the network? That's actually the next slide, so good anticipation. So if we draw this exact same visualization for the intermediate convolutional layers, it's actually a lot less interpretable. So this is performing the exact same visualization. So remember, so this is using the tiny ConvNet.js demo network that's running on the course website whenever you go there. So for that network, the first layer is a 7x7 convolution with 16 filters. So up at the top, we're visualizing these first layer weights for this network, just like we saw in the previous slide. But now the second layer weights, after we do a convolution, then there's some ReLU and some other nonlinearity perhaps. But the second convolutional layer now receives this 16-channel input and does a 7x7 convolution with 20 convolutional filters. And we've actually, so the problem here is that you can't really visualize these directly as images. So you can try. So here, if you, this 16 by, so the input is this, has 16 dimensions in depth. And we have these convolutional filters. Each convolutional filter is 7x7 and is extending along the full depth, so it has 16 elements. And then we have 20 such of these convolutional filters that are producing the output planes of the next layer. But the problem here is that we can't, looking directly at the weights of these filters doesn't really tell us much. So that's what we've done here, is that now for this single 16 by 7x7 convolutional filter, we can spread out those 16 7x7 planes of the filter into 16 7x7 grayscale images. So that's what we've done up here, which is these little tiny grayscale images here show us what are the weights in one of the convolutional filters at the second layer. And now, because there are 20 outputs from this layer, then this second convolutional layer has 20 such of these 16 by 16 or 16 by 7x7 filters. So if we visualize the weights of those convolutional filters as images, you can see that there's some kind of spatial structure here, but it doesn't really give you a good intuition for what they're looking at, because these filters are not connected directly to the input image. Instead, recall that the second layer convolutional filters are connected to the output of the first layer. So this is giving you a visualization of what type of activation pattern after the first layer convolution would cause the second layer convolution to maximally activate. But that's not very interpretable because we don't have a good sense for what those first layer convolutions look like in terms of image pixels. So we'll need to develop some slightly more fancy techniques to get a sense for what's going on in the intermediate layers. Question in the back? Yeah, so the question is that for all the visualizations on this and the previous slide, we've had to scale the weights to the 0 to 255 range. So in practice, those weights could be unbounded. They could have any range. But to get nice visualizations, we need to scale those. These visualizations also do not take into account the biases in these layers. So you should keep that in mind and not take these types of visualizations too literally. Now, at the last layer, remember when we're looking at the last layer of a convolutional network, we have these maybe 1,000 class scores that are telling us what are the predicted scores for each of the classes in our training data set. And immediately before that last layer, we often have some fully connected layer. In the case of AlexNet, we have some 4096 dimensional feature representation of our image that then gets fed into that final affine layer to predict our final class scores. And another kind of route for tackling the problem of visualizing and understanding convnets is to try to understand what's happening at the last layer of our convolutional network. So what we can do is take some data set of images, run a bunch of images through our trained convolutional network, and record that 4096 dimensional vector for each of those images. And now go through and try to figure out and visualize that last layer, that last hidden layer, rather than the first convolutional layer. So one thing you might imagine is trying a nearest neighbor approach. So remember, way back in the second lecture, we saw this graphic on the left where we had a nearest neighbor classifier where we were looking at nearest neighbors in pixel space between CFAR10 images. And then when you look at nearest neighbors in pixel space between CFAR10 images, you see that you pull up images that look quite similar to the query image. So again, on the left column here is some test image from the CFAR10 dataset. And then these next 5 columns are showing the nearest neighbors in pixel space to those test set images. And so, for example, this white dog that you see here, its nearest neighbors are all in pixel space are these kinds of white blobby things that may or may not be dogs, but at least the raw pixels of the image are quite similar. So now we can do the same type of visualization, computing and visualizing these nearest neighbor images, but rather than computing the nearest neighbors in pixel space, instead we can compute nearest neighbors in that 4096 dimensional feature space, which is computed by the convolutional network. So here on the right, we see some examples. So this first column shows us some examples of images from the test set of the ImageNet classification data set. And now these subsequent columns show us nearest neighbors to those test set images in the 4096 dimensional feature space computed by AlexNet. And you can see here that this is quite different from the pixel space nearest neighbors because the pixels are often quite different between the image and its nearest neighbors in feature space. However, the semantic content of those images tends to be similar in this feature space. So for example, if you look at this second layer, the query image is this elephant standing on the left side of the image with this green grass behind him. And now its third nearest neighbor in the test set is actually an elephant standing on the right side of the image. So this is really interesting because between this elephant standing on the left and this elephant standing on the right, the pixels between those two images are almost entirely different. However, in the feature space, which is learned by the network, those two images end up being very close to each other, which means that somehow this last layer of features is capturing some of the semantic content of these images. So that's really cool and really exciting. And in general, looking at these kind of nearest neighbor visualizations is a really quick and easy way to visualize something about what's going on here. Yeah, so the question is that through the standard supervised learning procedure for training classification networks, there's nothing in the loss encouraging these features to be close together. So that's true. It's just kind of a happy accident that they end up being close to each other because we didn't tell the network during training these features should be close. However, sometimes people do train networks using things called either a contrastive loss or a triplet loss, which actually explicitly make assumptions and constraints on the network such that those last layer features end up having some metric-based interpretation. But AlexNet, at least, was not trained specifically for that. Is what does this nearest neighbor thing have to do with the last layer? So we're taking this image, we're running it through the network, and then the second to last, like the last hidden layer of the network is a 4096 dimensional vector because there are these fully connected layers at the end of the network. So what we're doing is we're writing down that 4096 dimensional vector for each of the images, and then we're computing nearest neighbors according to that 4096 dimensional vector, which is computed by the network. Maybe we can chat offline. So another angle that we might have for visualizing what's going on in this last layer is by some concept of dimensionality reduction. So those of you who have taken CS229, for example, you've seen something like PCA, which lets you take some high-dimensional representation, like these 4096 dimensional features, and then compress it down to 2 dimensions, so then you can visualize that feature space more directly. So principal component analysis, or PCA, is kind of one way to do that. But there's another really powerful algorithm called TSNE, standing for T-distributed stochastic neighbor embeddings, which is a slightly more powerful method, which is a nonlinear dimensionality reduction method that people in deep learning often use for visualizing features. So here, as just an example of what TSNE can do, this visualization here is showing a TSNE dimensionality reduction on the MNIST dataset. So MNIST, remember, is this data set of handwritten digits between 0 and 9. Each image is a grayscale image, a 28 by 28 grayscale image. And now we've used TSNE to take that 28 times 28 dimensional feature space of the raw pixels for MNIST and now compress it down to 2 dimensions, and then visualize each of those MNIST digits in this compressed 2-dimensional representation. And when you run TSNE on the raw pixels in MNIST, you can see these natural clusters appearing, which corresponds to the digits of this MNIST data set. So now we can do a similar type of visualization where we apply this TSNE dimensionality reduction technique to the features from the last layer of our trained ImageNet classifier. So to be a little bit more concrete here, what we've done is that we take a large set of images, we run them all through our convolutional network, we record that final 4096 dimensional feature vector from the last layer for each of those images, which gives us a large collection of 4096 dimensional vectors. Now we apply TSNE dimensionality reduction to sort of compress that 4096 dimensional feature space down into a 2-dimensional feature space. And now we lay out a grid in that compressed 2-dimensional feature space and visualize what types of images appear at each location in the grid in this 2-dimensional feature space. So by doing this, you get some very coarse, rough sense of what the geometry of this learned feature space looks like. So these images are a little bit hard to see, so I'd encourage you to check out the high-resolution versions online. But at least maybe on the left, you can see that there's sort of one cluster in the bottom here of green things and different types of flowers. And there's other types of clusters for different types of dog breeds and other types of animals and locations. So there's sort of this continuous semantic notion in this feature space, which we can explore by looking through this t-SNE dimensionality reduction version of the features. Was there a question? Yeah, so the basic idea is that we have an image, so now we end up with 3 different pieces of information about each image. We have the pixels of the image, we have the 4096 dimensional vector, then we use t-SNE to convert the 4096 dimensional vector into a 2-dimensional coordinate, and then we take the original pixels of the image and place it at the 2-dimensional coordinate corresponding to the dimensionality reduced version of the 4096 dimensional feature. Yeah, a little bit involved here. Question in the front? Question is roughly how much variance do these 2 dimensions explain? Well, I'm not sure of the exact number, and it gets a little bit muddy when you're talking about t-SNE because it's a nonlinear dimensionality reduction technique. So I'd have to look offline, and I'm not sure of exactly how much it explains. Question? Can you do the same analysis at other layers of the network? And yes, you can, but no, I don't have those visualizations here. Sorry. Question? The question is, shouldn't we have overlaps between images once we do this dimensionality reduction? And yes, of course you would. So this is just kind of taking a nearest neighbor in a regular grid and then picking an image close to that grid point. So there's definitely this is not showing you the kind of density in different parts of the feature space. So that's another thing to look at. And again, at the link, there's a couple more visualizations of this nature that address that a little bit. Okay. So another thing that you can do for some of these intermediate features is, so we talked a couple slides ago that visualizing the weights of these intermediate layers is not so interpretable. But actually visualizing the activation maps of those intermediate layers is kind of interpretable in some cases. So again, in the example of AlexNet, remember the conv5 layer of AlexNet gives us this 128 by the conv5 features for any image is now a 128 by 13 by 13 dimensional tensor. But we can think of that as 128 different 13 by 13 2D grids. So now we can actually go and visualize each of those 13 by 13 elements, slices of the feature map as a grayscale image. And this gives us some sense for what types of things in the input are each of those features in that convolutional layer looking for. So this is a really cool interactive tool by Jason Yasinski that you can just download. So so I don't have the video, there's a video on his website, but it's running a convolutional network on the input stream of a webcam, and then visualizing in real time each of those slices of that intermediate feature map to give you a sense of what it's looking for. And you can see that, so here the input image is this picture of him sitting, this picture of a person in front of the camera. And most of these intermediate features are kind of noisy, not much going on. But there's this one highlighted intermediate feature that is also shown larger here that seems that it's activating on the portions of the feature map corresponding to the person's face, which is really interesting. And that kind of suggests that maybe this particular slice of the feature map of this layer of this particular network is maybe looking for human faces or something like that, which is kind of a nice and cool finding. Question? Are the black activations dead ReLUs? So you got to be a little careful with terminology. We usually say dead ReLU to mean something that's dead over the entire training data set. Here, I would say that it's a ReLU that's not active for this particular input. Question? The question is, if there's no humans in ImageNet, how can it recognize a human face? There definitely are humans in ImageNet. I don't think it's not one of the I don't think it's one of the 1,000 categories for the classification challenge, but people definitely appear in a lot of these images. And that can be a useful signal for detecting other types of things. So that's actually kind of a nice result because that shows that it sort of can learn features that are useful for the classification task at hand that are even maybe a little bit different from the explicit classification task that we told it to perform. So that's actually a really cool result. Okay, question? At each layer in the convolutional network, our input image is like 3 by 224 by 224, and then it goes through many stages of convolution. And then after each convolutional layer is some three-dimensional chunk of numbers, which are the outputs from that layer of the convolutional network. And that entire three-dimensional chunk of numbers, which are the output of the previous convolutional layer, we call like an activation volume. And then one of those slices is an activation map. The question is, if the image is k by k, will the activation map be k by k? Not always, because there can be subsampling due to strata convolution and pooling. But in general, the size of each activation map will be linear in the size of the input image. So another kind of useful thing we can do for visualizing intermediate features is visualizing what types of patches from input images cause maximal activation in different neurons. So what we've done here is that we pick maybe again the Con5 layer from AlexNet, and remember each of these activation volumes at Con5 and AlexNet gives us a 128 by 13 by 13 chunk of numbers. Then we'll pick one of those 128 channels, maybe channel 17. And now what we'll do is run many images through this convolutional network, and then for each of those images, record the Con5 features, and then look at the look at the parts of that 17th feature map that are maximally activated over our data set of images. And now, because again, this is a convolutional layer, each of those neurons in the convolutional layer has some small receptive field in the input. Each of those neurons is not looking at the whole image. They're only looking at some subset of the image. So then what we'll do is visualize the patches from this large data set of images corresponding to the maximal activations of that particular feature in that particular layer. And then we can sort these patches by their activation at that particular layer. So here is some examples from this network called the network doesn't matter. But these are some visualizations of these kind of maximally activating patches. So each row we've chosen one neuron from one layer of a network, and then they're sorted of these are the patches from some large data set of images that maximally activated this one neuron. And these can give you a sense for what types of features these neurons might be looking for. So for example, this top row, we see a lot of circly kinds of things in the image. Some eyes, mostly eyes, but also this kind of blue circly region. So then maybe this particular neuron in this particular layer of this network is looking for kind of blue circly things in the input. Or maybe in the middle here, we have neurons that are looking for text in different colors, or maybe curving edges of different colors and orientations. Question? So I've been a little bit loose with terminology here. So I'm saying that a neuron is one scalar value in that Con5 activation map. But because it's convolutional, all the neurons in one channel are all using the same weights. So we've chosen one channel, and then, right? So you get a lot of neurons for each convolutional filter at any one layer. So so these patches could have been drawn from anywhere in the image due to the convolutional nature of the thing. And now at the bottom, we also see some maximally activating patches for neurons from a higher up layer in the same network. And now because they're coming from higher in the network, they have larger receptive fields, so they're looking at larger patches of the input image. And we can also see that they're looking for maybe larger structures in the input image. So this second row is maybe it seems to be looking for humans or maybe human faces. We have maybe something looking for parts of cameras or different types of larger object-like types of things. Another cool experiment we can do that comes from Zeiler and Fergus ECCV 2014 paper is this idea of an occlusion experiment. So what we want to do is figure out which parts of the input image cause the network to make its classification decision. So what we'll do is we'll take our input image, in this case an elephant, and then we'll block out some region in that input image and just replace it with the mean pixel value from the data set. And now run that occluded image through the network, and then record what is the predicted probability of this occluded image. And now slide this occluded patch over every position in the input image, and then repeat the same process. And then draw this heat map showing what was the predicted probability output from the network as a function of which part of the input image did we occlude. And the idea is that if when we block out some part of the image, if that causes the network score to change drastically, then probably that part of the input image was really important for the classification decision. So here we've shown, I've shown 3 different examples of this occlusion type experiment. So maybe this example of a go-kart at the bottom, you can see over here that so here the red corresponds to a low probability and the white and yellow corresponds to a high probability. So when we block out the region of the image corresponding to this go-kart in front, then the predicted probability for the go-kart class drops a lot. So that gives us some sense that the network is actually caring a lot about these pixels in the input image in order to make its classification decision. Question? Yeah, so the question is that what's going on in the background. So maybe the image is a little bit too small to tell, but this is actually a go-kart track, and there's a couple other go-karts in the background. So I think that when you're blocking out these other go-karts in the background, that's also influencing the score. Or maybe like the horizon is there, and maybe the horizon is a useful feature for detecting go-karts. It's a little bit hard to tell sometimes. But this is a pretty cool visualization. Yeah, was there another question? Question is, sorry, what was the first question? So for this example, we're taking one image and then masking all parts of one image. The second question was, how is this useful? It's not maybe, you don't really take this information and loop it directly into the training process. Instead, this is a tool for humans to understand what types of computations these trained networks are doing. So it's more for your understanding than for improving performance per se. So another related idea is this concept of a saliency map, which is something that you will see in your homeworks. So again, we have the same question of, given an input image of a dog in this case, and the predicted class label of dog, we want to know which pixels in the input image are important for classification. We saw masking is one way to get at this question, but saliency maps are another angle for attacking this problem. And the question is, and one relatively simple idea from Karen Simonian's paper a couple years ago is just computing the gradient of the predicted class score with respect to the pixels of the input image. And this will directly tell us, in this sort of first order approximation sense, for each pixel in the input image, if we wiggle that pixel a little bit, then how much will the classification score for the class change? And this is another way to get at this question of which pixels in the input matter for the classification. And when we run, for example, compute a saliency map for this dog, we see kind of a nice outline of a dog in the image, which tells us that these are probably the pixels that network is actually looking at for this image. And when we repeat this type of process for different images, we get some sense that the network is sort of looking at the right regions, which is somewhat comforting. Question? The question is, do people use saliency maps for semantic segmentation? The answer is yes. That actually was, yeah, you guys are like really on top of it this lecture. So that was another component, again, in Karen's paper, where there's this idea that maybe you can use these saliency maps to perform semantic segmentation without any labeled data for these segments. So here they're using this grab cut segmentation algorithm, which I don't really want to get into the details of, but it's kind of an interactive segmentation algorithm that you can use. So then when you combine this saliency map with this grab cut segmentation algorithm, then you can, in fact, sometimes segment out the object in the image, which is really cool. However, I'd like to point out that this is a little bit brittle. And in general, this will probably work much, much, much worse than a network which did have access to supervision at training time. So I'm not sure how practical this is, but it is pretty cool that it works at all. But it probably works much less than something trained explicitly to segment with supervision. So kind of another related idea is this idea of guided backpropagation. So again, we still want to answer the question of, for one particular image, then now instead of looking at the class score, we want to know, we want to pick some intermediate neuron in the network and ask, again, which parts of the input image influence the score of that internal neuron in the network. And then you could imagine, again, computing a saliency map for this, again, right? that rather than computing the gradient of the class score with respect to the pixels of the image, you could compute the gradient of some intermediate value in the network with respect to the pixels of the image. And that would tell us, again, which pixels in the input image influence that value of that particular neuron. And that would be using normal backpropagation. But it turns out that there's a slight tweak that we can do to this backpropagation procedure that ends up giving some slightly cleaner images. So that's this idea of guided backpropagation that, again, comes from Zeiler and Fergus's 2014 paper. And I don't really want to get into the details too much here, but it's kind of a weird tweak where you change the way that you backpropagate through ReLU nonlinearities. And you sort of only backpropagate positive gradients through ReLUs, and you do not backpropagate negative gradients through the ReLUs. So you're no longer computing the true gradient. Instead, you're kind of only keeping track of positive influences throughout the entire network. So maybe you should read through these papers referenced here if you want a little bit more details about why that's a good idea. But empirically, when you do guided backpropagation as opposed to regular backpropagation, you tend to get much cleaner, nicer images that tell you which pixels of the input image influence that particular neuron. So again, we're seeing the same visualization that we saw a few slides ago of the maximally activating patches for different neurons in this convolutional network. But now, in addition to visualizing these maximally activating patches, we have also performed guided backpropagation to tell us exactly which parts of these patches influence the score of that neuron. So remember, for this example at the top, we saw that we thought this neuron is maybe looking for circle-y type things in the input patch because there were a lot of circle-y type patches. Well, when we look at guided backpropagation, we can see that that intuition is somewhat confirmed because it is indeed the circle-y parts of that input patch which are influencing that neuron's value. So this is kind of a useful tool for synthesizing, for understanding what these different intermediates are looking for. But one kind of interesting thing about guided backpropagation or computing saliency maps is that they are always a function of some fixed input image, right? They're telling us for a fixed input image which pixels or which parts of that input image influence the value of the neuron. Another question you might answer is remove this reliance on some input image and instead just ask what type of input in general would cause this neuron to activate. And we can answer this question using a technique called gradient ascent. So remember, we always use gradient descent to train our convolutional networks by minimizing the loss. Instead, now we want to fix the weights of our trained convolutional network and instead synthesize an image by performing gradient ascent on the pixels of the image to try and maximize the score of some intermediate neuron or of some class. So in the process of gradient ascent, we're no longer optimizing over the weights of the network. Those weights remain fixed. Instead, we're trying to change the pixels of some input image to cause this neuron or this neuron value or this class score to be maximized. But in addition, we need some regularization term. So remember, we've before seen regularization terms to try to prevent the network weights from overfitting to the training data. Now we need something kind of similar to prevent the pixels of our generated image from overfitting to the peculiarities of that particular network. So here, we'll often incorporate some regularization term that we want our generated image to have two properties. One, we want it to maximally activate some score or some neuron value, but we also want it to look like a natural image. And we want it to kind of have the kind of statistics that we typically see in natural images. So these regularization term in this objective is something to enforce our generated image to look relatively natural. And we'll see a couple different examples of regularizers as we go through. But the general strategy for this is actually pretty simple, and you'll, again, implement a lot of things of this nature on your assignment 3. But what we'll do is start with some initial image, either initializing to zeros or to uniform or Gaussian noise, but initialize your image in some way. And now repeat, where you'll forward your image through your network and compute the score or neuron value that you're interested. Now backpropagate to compute the gradient of that neuron score with respect to the pixels of the image, and then make a small gradient descent or gradient ascent update to the pixels of the image itself to try and maximize that score. And now repeat this process over and over again until you have a beautiful image. And then we talked about this image regularizer, Well, a very simple idea for an image regularizer is simply to penalize the L2 norm of our generated image. This is not so semantically meaningful. It just does something. And this was one of the earliest regularizers that we've seen in the literature for these type of generating images type papers. And when you run this on a trained network, you can see that now we're trying to generate images that maximize the dumbbell score in the upper left-hand corner here, for example. And then you can see that this synthesized image, I mean, it's a little bit hard to see maybe, but there are a lot of different dumbbell-like shapes, all kind of superimposed at different portions of the image. Or if we try to generate an image for cups, then we can maybe see a bunch of different cups all kind of superimposed. The Dalmatian is pretty cool because now we can kind of see this black and white spotted pattern that's kind of characteristic of Dalmatians. Or for lemons, we can see these different kinds of yellow splotches in the image. And there's a couple of more examples here. I think maybe the goose is kind of cool. Or the kit fox actually maybe looks like a kit fox. Question? The question is why are these all rainbow colored? And in general, getting true colors out of these visualizations is pretty tricky, right? Because any actual image will be bounded in the range 0 to 255, so it really should be some kind of constrained optimization problem. But if we're using these generic methods for gradient ascent, then that's kind of an unconstrained problem. So you maybe use like a projected gradient ascent algorithm, or you'll rescale the image at the end. So the colors that you see in these visualizations, sometimes you can't take them too seriously. Question? Question is, what happens if you let the thing loose and don't put any regularizer on it? Well, then you tend to get an image which maximizes the score, which is confidently classified as the class you wanted, but usually it doesn't look like anything. It kind of looks like random noise. So that's kind of an interesting property in and of itself that we'll go into much more detail in a future lecture. But that's why, but that kind of doesn't help you so much for understanding what things the network is looking for. So if we want to understand why the network makes its decisions, then it's kind of useful to put a regularizer on there to force the generated image to look more natural. Question in the back? Yeah, so the question is that we see a lot of multimodality here, and are there ways to combat that? And actually, yes, we'll see that this is kind of the first step, and there's a whole line of work at improving these visualizations. So another kind of, so then the angle here is kind of to improve the regularizer to improve our visualized images. And there was another paper from Jason Yasinski and some of his collaborators where they added some additional implicit regularizers. So in addition to this L2 norm constraint, in addition, we'll also periodically during optimization do some Gaussian blurring on the image, or also clip some small pixel values all the way to 0, or also clip some of the pixel values with low gradients to 0. So you can see this as kind of a projected gradient descent algorithm, where at each periodically we're projecting our generated image onto some nicer set of images with some nicer properties. For example, spatial smoothness with respect to the Gaussian blurring. So when you do this, you tend to get much nicer images that are much clearer to see. So now these flamingos look like flamingos. The ground beetle is starting to look more beetle-like. Or this black swan maybe looks like a black swan. These billiard tables actually look kind of impressive now, where you can definitely see this billiard table structure. So you can see that once you add in nicer regularizers, then the generated images become a little bit cleaner. And now we can perform this procedure not only for the final class scores, but also for these intermediate neurons as well. So instead of trying to maximize our billiard table score, for example, instead we can try to maximize one of the neurons from some intermediate layer. Question? So the question is, what's with the 4 examples here? So remember, we're initializing our image randomly. So these 4 images would be different random initializations of the input image. And again, we can use this same type of procedure to visualize, to synthesize images which maximally activate intermediate neurons of the network. And then you can get a sense for what some of these intermediate neurons are looking for. So maybe at layer 4, there's this neuron that's kind of looking for spirally things, or this neuron that's maybe looking for like chunks of caterpillars. It's a little bit hard to tell. But generally, as you go larger up in the image, then you can see that obviously the receptive fields of these neurons are larger, so they're looking at larger patches in the image, and they tend to be looking for maybe larger structures or more complex patterns in the input image. So that's pretty cool. And then people have really gone crazy with this and trying to basically improve these visualizations by heaping on extra features. So this was a cool paper, this whole paper was kind of explicitly trying to address this multimodality that someone asked a question about a few minutes ago. So here they were trying to explicitly take this multimodality into account in the optimization procedure, where they did indeed, I think, seed the initial, for each of the classes, you run a clustering algorithm to try to separate the classes into different modes, and then initialize with something that is close to one of those modes. And then when you do that, you kind of account for this multimodality. So for intuition, on the right here, these eight images are all of grocery stores, but the top row is kind of close-up pictures of produce on the shelf, and those are labeled as grocery store in ImageNet. And the bottom row kind of shows people walking around grocery stores or at the checkout line or something like that. And those are also labeled as grocery store, but their visual appearance is quite different. So a lot of these classes end up being sort of multimodal. And if you explicitly take this multimodality into account when generating images, then you can get nicer results. And now, then when you look at some of their example synthesized images for classes, you can see like the bell pepper, the cardon, strawberries, jack-o'-lantern, that now they end up with some very beautiful generated images. And now I don't want to get too much into detail of the next slide, but then you can even go crazier and add an even stronger image prior and generate some very beautiful images indeed. So these are all synthesized images that are trying to maximize the class score of some ImageNet class. But the general idea is that rather than optimizing directly the pixels of the input image, instead they're trying to optimize the FC6 representation of that image instead. And now they need to use some feature inversion network, and I don't want to get into the details here. You should read the paper. It's actually really cool. But the point is that when you start adding additional priors towards modeling natural images, then you can end up generating some quite realistic images that give you some sense of what the network is looking for. So that's sort of one cool thing that we can do with this strategy. But this idea of trying to synthesize images by using gradients on the image pixels is actually super powerful. And another really cool thing we can do with this is this concept of a fooling image. So what we can do is pick some arbitrary image and then try to maximize so say we've taken a picture of an elephant, and then we tell the network that we want to change the image to maximize the score of koala bear instead. So then what we're doing is trying to change that image of an elephant to try and instead cause the network to classify it as a koala bear. And what you might hope for is that maybe that elephant would sort of start morphing into a koala bear, and maybe he would sprout little cute ears or something like that. But that's not what happens in practice, which is pretty surprising. Instead, if you take this picture of an elephant and try to change the elephant image to instead cause it to be classified as a koala bear, what you'll find is that this second image on the right actually is classified as koala bear, but it looks the same to us. So that's pretty fishy and pretty surprising. So also on the bottom, we've taken this picture of a boat. Schooner is the ImageNet class. And then we told the network to classify it as an iPod. So now the second example still looks like a boat to us, but the network thinks it's an iPod. And the differences in pixels between these two images are basically nothing. And if you magnify those differences, you don't really see any iPod or koala-like features on these differences. They're just kind of like random patterns of noise. So the question is, what's going on here, and like, how can this possibly be the case? Well, we'll have a guest lecture from Ian Goodfellow in a week and a half, 2 weeks. And he's going to go in much more detail about this type of phenomenon, and that'll be really exciting. But I did want to mention it here because it is on your homework. Question? That's something, so the question is, can we use fooled images as training data? And I think Ian's going to go in much more detail on all of these types of strategies, because that's really a whole lecture unto itself. Question? the question is, why do we care about any of this stuff, basically? uh, okay, maybe that was a mischaracterization, I'm sorry. Question is, what does understanding these intermediate neurons, how does that help our understanding of the final classification? This is actually, this whole field of trying to visualize intermediates is kind of in response to a common criticism of deep learning. So a common criticism of deep learning is like, you've got this big black box network, you trained it on gradient descent, you get a good number, and that's great, but we don't trust the network because we don't understand as people why it's making the decisions that it's making. So a lot of these type of visualization techniques were developed to try and address that and try to understand as people why the networks are making their various classification decisions a bit more. Because if you contrast a deep convolutional neural network with other machine learning techniques, like linear models are much easier to interpret in general because you can look at the weights and kind of understand the interpretation between how much each input feature affected the decision. Or if you look at something like a random forest or a decision tree, some other machine learning models end up being a bit more interpretable just by their very nature than these large sort of black box convolutional networks. So a lot of this is sort of in response to that criticism to say that, yeah, yes, they are these large complex models, but they are still doing some interesting and interpretable things under the hood. They're not just totally going out and randomly classifying things. They are doing something meaningful. So another cool thing we can do with this gradient-based optimization of images is this idea of deep dream. So this was a really cool blog post that came out from Google a year or two ago. And the idea is that so we talked about scientific value. This is almost entirely for fun. So the point of this exercise is mostly to generate cool images. And kind of as a side, you also get some sense for what features images are looking at, or these networks are looking at. So what we can do is we take our input image, we run it through the convolutional network up to some layer, and now we backpropagate and set the gradient of that at that layer equal to the activation value. And now backpropagate back to the image, update the image, and repeat, repeat, repeat. So this has the interpretation of trying to amplify existing features that were detected by the network in this image, right? Because whatever features existed on that layer, now we set the gradient equal to the feature, and we just tell the network to amplify whatever features you already saw in that image. And by the way, you can also see this as trying to maximize the L2 norm of the features at that layer of the image. When you do this, the code ends up looking really simple. So your code for many of your homework assignments will probably be about this complex, or maybe even a little bit less so. So the idea is that, but there's a couple tricks here that you'll also see in your assignments. So one trick is to jitter the image before you compute your gradients. So rather than running the exact image through the network, instead you'll shift the image over by 2 pixels and kind of wrap the other 2 pixels over here. And this is a kind of regularizer to prevent each of these, it regularizes a little bit to encourage a little bit of extra spatial smoothness in the image. You'll also see they use L1 normalization of the gradients. That's kind of a useful trick sometimes when doing these image generation problems. You'll also see them clipping the pixel values once in a while. So again, we talked about images actually should be between 0 to 255. So this is a kind of projected gradient descent where we project onto the space of actual valid images. But now when we do all this, then we might start with some image of a sky, and then we get really cool results like this. So you can see that now we've taken these tiny features on the sky, and they get amplified through this process. And we can see things like these different mutant animals start to pop up, or these kind of spiral shapes pop up. Different kinds of houses and cars pop up. So that's all pretty interesting. There's a couple patterns in particular that pop up all the time that people have named. Right? So there's this admiral dog that shows up a lot. There's the pig snail, the camel bird, the dogfish. Right? So these are kind of interesting. But actually, the fact that dogs show up so much in these visualizations actually does tell us something about the data on which this network was trained. Right? Because this is a network that was trained for ImageNet classification. ImageNet has 1,000 categories, but 200 of those categories are dogs. So, so it's kind of not surprising in a sense that when you do these kind of visualizations, the network ends up hallucinating a lot of dog-like stuff in the image, often morphed with other types of animals. When you do this at other layers of the network, you get other types of results. So here we're taking one of these lower layers in the network. The previous example was relatively high up in the network. And now, again, we have this interpretation that lower layers are maybe computing edges and swirls and stuff like that, and that's kind of borne out when we run Deep Dream at a lower layer. Or if you run this thing for a long time and maybe add in some multi-scale processing, you can get some really, really crazy images, right? So here they're doing a kind of multi-scale processing where they start with a small image, run Deep Dream on the small image, then make it bigger and continue Deep Dream on the larger image and kind of repeat with this multi-scale processing. And then you can get, and then maybe after you complete the final scale, then you restart from the beginning and you just go wild on this thing. And you can get some really crazy images. So these examples were all from networks trained on ImageNet. There's another data set from MIT called the MIT Places data set that instead of 1,000 categories of objects, instead it's 200 different types of scenes, like bedrooms and kitchens and stuff like that. And now if we repeat this Deep Dream procedure using a network trained on MIT Places, we get some really cool visualizations as well. So now instead of dog slugs and admiral dogs and this kind of stuff, instead we often get these kind of roof shapes of these kind of Japanese-style buildings, or these different types of bridges or mountain ranges, like really, really cool, beautiful visualizations. So the code for Deep Dream is online, released by Google. You can go check it out and make your own beautiful pictures. So there's another kind of, sorry, question? So the question is, what are we taking gradient of? So like I said, because like 1 over x squared, the gradient of that is x. So if you send back the volume of activations as the gradient, that's equivalent to taking the gradient with respect to the like 1 over x squared sum of the values. So it's equivalent to maximizing the norm of the features at that layer. But in practice, many implementations you'll see not explicitly compute that. Instead, they'll just send the gradient back. So another kind of useful thing that we can do is this concept of feature inversion. So this again gives us a sense for what types of elements of the image are captured at different layers of the network. So what we're going to do now is we're going to take an image, run that image through the network, record the feature value for one of those images, and now we're going to try to reconstruct that image from its feature representation. And the question, and now based on how much, like what that reconstructed image looks like, that'll give us some sense for what type of information about the image was captured in that feature vector. So again, we can do this with gradient descent with some regularizer, where now rather than maximizing some score, instead we want to minimize the distance between this cached feature vector and between the computed features of our generated image to try and, again, synthesize a new image that matches the feature vector that we computed before. And another kind of regularizer that you frequently see here is the total variation regularizer that you'll also see on your homework. So here, the total variation regularizer is penalizing differences between adjacent pixels, both adjacent in left and right and adjacent top to bottom, to again try to encourage spatial smoothness in the generated image. So now, if we do this idea of feature inversion, so this visualization here, on the left, we're showing some original image, the elephants or the fruit at the left. And then we run the image through a VGG16 network, record the features of that network at some layer, and then try to synthesize a new image that matches the recorded features at that layer. And this kind of gives us a sense for how much information is stored in these images, in these features at different layers. So for example, if we try to reconstruct the image based on the ReLU 2.2 features from VGG16, we see that the image gets almost perfectly reconstructed, which means that we're not really throwing away much information about the raw pixel values at that layer. But as we move up into the deeper parts of the network and try to reconstruct from ReLU 4.3, ReLU 5.1, we see that our reconstructed image now we've kind of kept the general spatial structure of the image. You can still tell that it's an elephant or a banana or an apple, but a lot of the low-level details around exactly what the pixel values were and exactly what the colors were, exactly what the textures were, these kind of low-level details are kind of lost at these higher layers of the network. So that gives us some sense that maybe as we move up through the layers in the network, it's kind of throwing away this low-level information about the exact pixels of the image, and instead is maybe trying to keep around a little bit more semantic information that's a little bit invariant to small changes in color and texture and things like that. So we're building towards style transfer here, which is really cool. So in addition to understand style transfer, in addition to feature inversion, we also need to talk about a related problem called texture synthesis. So in texture synthesis, this is kind of an old problem in computer graphics. Here the idea is that we're given some input patch of a texture, something like these little scales here, and now we want to build some model and then generate a larger piece of that same texture. So for example, we might here want to generate a large image containing many scales that kind of look like the input. And this is, again, a pretty old problem in computer graphics. There are nearest neighbor approaches to texture synthesis that work pretty well. So there's no neural networks here. Instead, this is kind of a simple algorithm where we march through the generated image 1 pixel at a time in scanline order, and then look at a neighborhood around the current pixel based on the pixels that we've already generated, and now compute a nearest neighbor of that neighborhood in the patches of the input image, and then copy over 1 pixel from the input image. So maybe you don't need to understand the details here. Just the idea is that there's a lot of classical algorithms for texture synthesis. It's a pretty old problem that you can do this without neural networks, basically. And when you run this kind of classical texture synthesis algorithm, it actually works reasonably well for simple textures. But as we move to more complex textures, these kinds of simple methods of maybe copying pixels from the input patch directly tend not to work so well. So in 2015, there was a really cool paper that tried to apply neural network features to this problem of texture synthesis, and ended up framing it as kind of a gradient ascent procedure, kind of similar to the various feature matching objectives that we've seen already. So in order to perform neural texture synthesis, they use this concept of a Graham matrix. So what we're going to do is we're going to take our input texture, in this case some pictures of rocks, and then take that input texture and pass it through some convolutional neural network and pull out the convolutional features at some layer of the network. So maybe then this convolutional feature volume that we've talked about might be h by w by c, or sorry, c by h by w at that layer of the network. So you can think of this as an h by w spatial grid, and at each point of the grid, we have this c-dimensional feature vector describing kind of the rough appearance of that image at that point. And now we're going to use this activation map to compute a descriptor of the texture of this input image. So what we're going to do is pick out 2 of these different feature columns in the input volume. Each of these feature columns will be a c-dimensional vector, and now take the outer product between those 2 vectors to give us a c by c matrix. This c by c matrix now tells us something about the co-occurrence of the different features at those 2 points in the image. Right? So if element ij in the c by c matrix is large, that means that both elements I and j of those 2 input vectors were large, and something like that. So this somehow captures some second-order statistics about which features in that feature map tend to activate together at different spatial volumes, or at different spatial positions. And now we're going to repeat this procedure using all different pairs of feature vectors from all different points in this h by w grid, average them all out, and that gives us our c by c Graham matrix. And this is then used as a descriptor to describe kind of the texture of that input image. So what's interesting about this Graham matrix is that it has now thrown away all spatial information that was in this feature volume, because we've averaged over all pairs of feature vectors at every point in the image. Instead, it's just capturing these second-order co-occurrent statistics between features. And this ends up being a nice descriptor for texture. And by the way, this is really efficient to compute. So if you have a c by h by w 3-dimensional tensor, you can just reshape it to c times h by w, and then takes that times its own transpose and compute this all in one shot. So it's super efficient. But you might be wondering why you don't use an actual covariance matrix or something like that instead of this funny Graham matrix. And the answer is that using true covariance matrices also works, but it's a little bit more expensive to compute. So in practice, a lot of people just use this Graham matrix descriptor. So then there's this, now once we have this sort of neural descriptor of texture, then we can use a similar type of gradient ascent procedure to synthesize a new image that matches the texture of the original image. So now this looks kind of like the feature reconstruction that we saw a few slides ago, but instead of trying to reconstruct the whole feature map from the input image, instead we're just going to try and reconstruct this Graham matrix texture descriptor of the input image instead. So in practice, what this looks like is that you'll download some pre-trained model, like in feature inversion. Often people will use the VGG networks for this. You'll take your texture image, feed it through the VGG network, compute the Graham matrix and many different layers of this network. Then you'll initialize your new image from some random initialization, and then it looks like gradient ascent again, just like for these other methods that we've seen. So you take that image, pass it through the same VGG network, compute the gram matrix at various layers, and now compute loss as the L2 norm between the gram matrices of your input texture and your generated image. And then you backprop and compute a gradient of the pixels on your generated image, and then make a gradient ascent step to update the pixels of your image a little bit. And now repeat this process many times. Go forward, compute your gram matrices, compute your losses, backprop, get gradients on the image, and repeat. And once you do this, eventually you'll end up generating a texture that matches your input texture quite nicely. So this was all from a NIPS 2015 paper by a group in Germany, and they had some really cool results for texture synthesis. So here on the top, we're showing 4 different input textures, and now on the bottom, we're showing doing this texture synthesis approach by gram matrix matching by computing the gram matrix at different layers of this pre-trained convolutional network. So you can see that if we use these very low layers in the convolutional network, then we kind of match we generally get splotches of the right colors, but the overall spatial structure doesn't get preserved so much. And now as we move to down farther in the image, and you compute these gram matrices at higher layers, you see that they tend to reconstruct larger patterns from the input image. For example, these whole rocks or these whole cranberries. And now this works pretty well, that now we can synthesize these new images that kind of match the general spatial statistics of their inputs, but they're quite different pixel-wise from the actual input itself. Question? Where do we compute the loss? And in practice, if you want to get good results, typically people will compute gram matrices at many different layers, and then the final loss will be a sum of all those, potentially a weighted sum. But I think for this visualization, to try to pinpoint the effect of the different layers, I think these were doing reconstruction from just one layer. So now something really, then they had a really brilliant idea kind of after this paper, which is, what if we do this texture synthesis approach, but instead of using an image like rocks or cranberries, what if we set it equal to a piece of artwork? So then, for example, if you do this same texture synthesis algorithm by maximizing gram matrices, but now we take, for example, Vincent van Gogh's Starry Night or The Muse by Picasso as our texture, as our input texture, and then run this same texture synthesis algorithm, then we can see that our generated images tend to reconstruct interesting pieces from those pieces of artwork. And now something really interesting happens when you combine this idea of texture synthesis by gram matrix matching with feature inversion by feature matching. And then this brings us to this really cool algorithm called style transfer. So in style transfer, we're going to take 2 images as input. One, we're going to take a content image that will guide like what type of thing we want, what we generally want our output to look like. Also a style image that will tell us what is the general texture or style that we want our generated image to have. And then we will jointly do we will generate a new image by minimizing the feature reconstruction loss of the content image and the gram matrix reconstruction loss of the style image. And when we do these 2 things, we get a really cool image that kind of renders the content image kind of in the artistic style of the style image. And now this is really cool. And you can get these really beautiful figures. So again, what this kind of looks like is that you'll take your style image and your content image, pass them into your network to compute your gram matrices and your features. And now you'll initialize your output image with some random noise, go forward, compute your losses, go backward, compute your gradients on the image, and repeat this process over and over, doing gradient ascent on the pixels of your generated image. And after a few hundred iterations, generally, you'll get a beautiful image. So I have an implementation of this online on my GitHub that a lot of people are using. And it's really cool. So this is kind of gives you a lot more control over the generated image as compared to Deep Dream, right? So in Deep Dream, you don't have a lot of control about exactly what types of things are going to happen coming out at the end. You just kind of pick different layers of the networks, maybe set different numbers of iterations, and then dog slugs pop up everywhere. But with style transfer, you get a lot more fine-grained control over what you want the result to look like, right? By now picking different style images with the same content image, you can generate a whole different types of results, which is really cool. Also, you can play around with the hyperparameters here, right? Because we're doing a joint we're minimizing this feature reconstruction loss of the content image and this gram matrix reconstruction loss of the style image. And if you trade off the weighting between those 2 terms and the loss, then you can get control about how much we want to match the content versus how much we want to match the style. There's a lot of other hyperparameters you can play with, For example, if you resize the style image before you compute the gram matrix, that can give you some control over what the scale of features are that you want to reconstruct from this style image. So you can see that here we've done this same reconstruction. The only difference is how big was the style image before we computed the gram matrix. And this gives you another axis over which you can control these things. You can also actually do style transfer with multiple style images if you just match sort of multiple gram matrices at the same time. And that's kind of a cool result. We also saw this multi-scale process. So another cool thing you can do, we talked about this multi-scale processing for Deep Dream and saw how multi-scale processing in Deep Dream can give you some really cool high-resolution results. And you can do a similar type of multi-scale processing in style transfer as well. So then we can compute images like this that are super high resolution. This is, I think, a 4K image of our favorite school, like rendered in the style of Starry Night. But this is actually super expensive to compute. I think this one took 4 GPUs, so a little expensive. We can also do other style images and get some really cool results from the same content image, again, at high resolution. Another fun thing you can do is, you can actually do joint style transfer and Deep Dream at the same time. So now we'll have 3 losses: the content loss, the style loss, and this Deep Dream loss that tries to maximize the norm. And you get something like this. So now it's Van Gogh with the dog slugs coming out everywhere. So that's really cool. But there's kind of a problem with these style transfer algorithms, which is that they're pretty slow, right? You need to compute a lot of forward and backward passes through your pre-trained network in order to compute these images. And especially for these high-resolution results that we saw in the previous slide, each forward and backward pass of a 4K image is going to take a lot of compute and a lot of memory. And if you need to do several hundred of those iterations, generating these images could take many, like tens of minutes, even on a powerful GPU. So it's really not so practical to apply these things in practice. The solution is to now train another neural network to do the style transfer for us. So I had a paper about this last year. And the idea is that we're going to fix some style that we care about at the beginning, in this case, Starry Night. And now, rather than running a separate optimization procedure for each image that we want to synthesize, instead, we're going to train a single feed-forward network that can input the content image and then directly output the stylized result. And now, the way that we train this network is that we compute these same content and style losses during training of our feed-forward network and use that same gradient to update the weights of the feed-forward network. And now this thing takes maybe a few hours to train, but once it's trained, then in order to produce stylized images, you just need to do a single forward pass through the trained network. So I have code for this online, and you can see that it ends up looking about relatively comparable quality in some cases to this very slow optimization-based method, but now it runs in real time. It's about 1,000 times faster. So here you can see this is like a demo of it running live off my webcam. So this is not running live right now, obviously, but if you have a big GPU, you can easily run 4 different styles in real time, all simultaneously, because it's so efficient. There was another group from Russia that had a very similar paper concurrently, and their results are about as good. They also had this kind of tweak on the algorithm. So this this feed-forward network that we're training ends up looking a lot like these segmentation models that we saw. So these segmentation networks for semantic segmentation, we're doing downsampling and then many layers, then some upsampling with transposed convolution in order to downsample and upsample to be more efficient. The only difference is that now this final layer produces a 3-channel output for the RGB of that final image. And inside this network, we have batch normalization in the various layers. But in this paper, they swap out the batch normalization for something else called instance normalization. It tends to give you much better results. So one drawback of these types of methods is that we are now training one new style transfer network for every style that we want to apply. So that could be kind of expensive if now you need to keep a lot of different trained networks around. So there was a paper from Google that just came pretty recently that addressed this by using one feed-forward trained network to apply many different styles to the input image. So now they can train one network to apply many different styles at test time using one trained network. So here, it's going to take the content image as input as well as the identity of the style that you want to apply. And then this is using one network to apply many different types of styles. And again, runs in real time. that same algorithm can also do this kind of style blending in real time with one trained network. So now once you've trained this network on these 4 different styles, you can actually specify a blend of these styles to be applied at test time, which is really cool. So these kinds of real-time style transfer methods are on various apps, and you can see these out in practice a lot now these days. So kind of the summary of what we've seen today is that we've talked about many different methods for understanding CNN representations. We talked about some of these activation-based methods like nearest neighbors, dimensionality reduction, maximal patches, occlusion images that try to understand, based on the activation values, what the features are looking for. We also talked about a bunch of gradient-based methods where you can use gradients to synthesize new images to understand your features, such as saliency maps, class visualizations, fooling images, feature inversion. And we also had fun by seeing how a lot of these similar ideas can be applied to things like style transfer and deep dream to generate really cool images. So next time, we'll talk about unsupervised learning, autoencoders, variational autoencoders, and generative adversarial networks. So that should be a fun lecture.